Hello, geometry students. Welcome back to section 10.7. So we're doing circles still, and we are going to take a look at special segments in a circle. So we still got chords or tangents or secants. However, in section 10.6, we talked about angles. I just want to make sure that I mention we are going to find the measures of segments. So not angles. So 10.6 is all about angles. 10.7 is all about segments. So we've got three specific situations that happen. So let's do each one, and we'll do an example so that you can see what they look like. So the first theorem says if two chords intersect in a circle. So please notice it's important that we see, just like we talked about in section 10.6, they intersect inside the circle. So if you notice on my example here on the right-hand side, chord DE and chord AC intersect at point B, and point B is inside the circle. So that's what it looks like. So if those two chords intersect inside the circle, then the products of the measures of the segments of the chords are equal. So what that means is the products of the segments. So multiply its products, right? So if I look at this particular example, if I take this whole chord, AB, and I multiply its two pieces. So AB times BC has to be equal to the other segment. It's product of its two pieces. So EB times BC, or sorry, times BD. So here's how I think of this. I'm going to say this a lot. When I look at one segment, chord AC, it is part times part is equal to the other segment, ED, the other chord, part times part. So that might be a little easier to follow. So in example 1, it says to find x. So notice, just about the same lettering, right? So I've got this chord CD. I know I'm going to set up an equation, so I'm going to take the two parts of chord CD. So 3 times 4. And then I've got this other chord over here, AB. I'm going to take the two parts of chord AB, x times 6. Super simple equation to solve here. So if 12 equals 6x, x must be equal to 2 when we divide both sides by 6. So part times part for each chord is equal to the other part times part. All right, so we just found out that this little segment AE has to be equal to 2. All right, so there's our first theorem. That's what happens when our two chords intersect inside a circle. When we look at this next one, we've got two secants that are drawn from to a circle from an exterior point. So my two secants AC and I'll just put segment and AE. Those are secants and they intersect at point A, and point A is outside the circle. It's an exterior point outside the circle. So we're looking for where those segments intersect. They intersect outside the circle. They happen to be called secants. So if those two secants are drawn to a circle from an exterior point, like point A, then the product of the measures of one secant segment and its exterior secant is equal to the product of the measures of the other secant segment and its external secant segment. Everybody's got that, right? Let's put this in normal terms. Here's what I've got. Just like we did on those chords, if we take those secants. So if I just look at this big secant, AC, what this theorem says is if you take the exterior part times the whole thing, that equals the other secant's exterior part times the whole thing. So AB times AC equals AD times AE. I prefer to think of it this way. Exterior times whole equals exterior times whole. So the outside part of that secant times the whole secant equals on the other one the exterior times the whole. So you just deal with one secant at a time. So it says on here to find RS for this example. So RS, I'm going to put a little X on there. If PQ is 12, so that's from P to Q, that's the chord inside the circle. QR is 2, that's my exterior segment. TS is 3, and RS is X. So if I'm going to go by this exterior times whole, so let's think about this first. The exterior part of secant PR, exterior times whole. The exterior is 2, right? Be careful on the whole. The whole thing from P to R has to be 14. So don't forget that sneaky little part. That's where you could get tripped up. So watch carefully on that one. On this side, my exterior part is X, and my whole, oh, this one's interesting, right? This has to be X plus 3 because I add the two parts together. I sense a quadratic coming on. Remember when we did quadratic formula or factoring? So I've got to go ahead and distribute and get everything equal to 0. So when I distribute on this side, well, I could do 28, right, equals. That would be x squared plus 3x. In order to solve this, I can't just square root because that x is 3x is throwing us for a little loop here. So I'm going to minus 28 from both sides. If it's equal to 0, you can factor, or you can do quadratic formula, whatever you prefer. For me, I think factoring's faster because, remember, I'm going to see what multiplies to a times c, adds to b. Well, a is 1, c is negative 28. So what multiplies to negative 28 and adds to 3, positive 3. Feels like it's going to be 7 times negative 4. Maybe you already knew that because 7 plus negative 4 equals that 3. Stick x's on both of those. Actually, you don't even need to do that. Let's just jump right to parentheses. Since our a value is 1, we can put our values in there. So I know if I'm going to FOIL or distribute this out, I know I have to have an x and an x in my first terms in each parenthesis. And then I'm going to take my numbers, my positive 7 and my negative 4, and those guys will FOIL out to get that x squared plus 3x minus 28. So remember, this is where we use the zero product property. Make each guy equal to 0 and ignore the other one. So if x plus 7 is equal to 0, when I subtract 7, x has to be negative 7. If x minus 4 is equal to 0, when I add 4 to both sides, x has to be equal to 4. Now a teeny bit of common sense has to set in. Can negative 7 be a possible answer for segment RS? We can't have a negative segment, right? So negative 7 is going to be junk. 4 would work. So 4 is going to be my only answer. You cannot have a negative segment, so you automatically take those out. So that was a good refresher for factoring. And again, if you need the quadratic formula, do a quick lookup and get that. You still use A's, B's, and C's. All right, so that's our second scenario. We've got two secants. They intersect outside the circle. So exterior times whole. Here's our third and final theorem. This one says if you've got a tangent and a secant drawn from an exterior point. So this time it's W is exterior, outside the circle. Then the square of the measure of the tangent is equal to the product of the measures of the secant segment and its external secant segment. I'm sure everybody's got that. What that's saying is you take your WX, your tangent squared, and set that equal to exterior times whole. If this seems hard to remember, or one more thing to remember, if you just look at that tangent segment, WX, we could technically say it's still the exterior part of that segment, so the segment that's outside the circle, times the whole segment. So technically, tangent squared is the same as exterior portion times whole. So we could say tangent squared here, or we could still say exterior times whole. They just happen to be the same piece. So whichever makes the most sense to you. To me, it's one less thing to remember if I just always remember exterior point, like W, means exterior times whole. All right, so let's run through a quick example here. Notice AB is the tangent on example 3. It says to find x. BD is the secant. So I'm going to do exterior times whole and tangent squared, or exterior times whole. So if I just look at this tangent, right, it is 4. From B to A is 4 units. So I know that is going to be 4 times 4, or 4 squared if you prefer, or we're going to end up with a 16 down here. Exterior portion of that purple segment is 4, and the whole thing is 4. Down here, exterior times whole, well, the exterior is x. The whole thing, your remembering thing to do is when you come for the whole segment, I should probably write this down. Whole segment, you typically are going to be given the 2 pieces. You need to add to get that. So basically, x plus 2 plus x would be 2x plus 2 for the whole thing. So exterior is x times 2x plus 2. All right, so I'm going to FOIL that out. I'm going to get 16 is equal to 2x squared plus 2x. It's a quadratic because I've got that 2x. I can't just divide by 2 or square root. So I'm going to minus 16 from both sides. So 0 equals 2x squared plus 2x minus 16. That's equal to 0. Let's do a quick quadratic formula on this one. Hopefully you've got this. X is equal to a negative b plus or minus a giant square root, b squared minus 4ac, all over 2a. Remember, a is your number out in front of your x squared, b, and c. So when I plug numbers in there, and sometimes it's easiest to just jot down your a, b, and c on the side, then you never have to think again. A is 2, b is positive 2, and c is a negative 16. Take the signs with those. So negative b would end up being negative 2 plus or minus a giant square root. Remember that plus or minus is where we get 2 possible answers. So 2 squared minus 4 times my a value, which is 2, times c, which is negative 16. And that's all going to be over 2 times 2. So let's see what we got here. We should have, I better grab my calculator, 2 squared. Remember, just do the discriminant. Just do the portion under the square root. Don't do the square root quite yet. I'm pretty sure when I did my math here, I got a not very nice answer. That tells me that this wouldn't have been factorable. There would be nothing that would multiply to a times c but add to b. I got a 132 underneath that square root sign. Take a pause and make sure that you get the same answer as I did, because that's kind of a big deal. So if I go to the 132, that's like, I'm going to go to the nearest 100, that's like an 11.49, I think. Yep, 11.49. So negative 2 plus or minus an 11.49 all over 4. We could leave this in exact terms. We do need to take a quick look at those numbers, though. So negative 2 plus 11.49, hit equals, and then divide by 4. Don't forget it's a 4. I got 2 possible answers here. So my negative 2 plus gave me a 2.37 roughly. Remember, this is rounded because that 11.49 is kind of junk. Negative 2 minus 11.49, hit equals, and then divide by 4. I believe that's a negative 3.37. Take a quick think about this. See if I can move these guys up. Probably not easily. So if I think about this in terms of my original diagram, could this little segment BC be a negative value? It can, right? So automatically I'm crossing out the negative. My only possible answer is 2.37. Not a nice answer, but an answer. Again, we could have kept that in terms of exact answers, broken down that 132, but it's a little bit harder to wrap your brain around. All right, so let's do a couple quick examples just to make sure everything's there. I know a lot of people use their examples. So number one, it says to find x. Oops, hold on one sec. Fire drill. Notice how these two chords are intersecting inside the circle. So if they're intersecting inside the circle, that means that we do part times part equals part times part, right? So I don't even have these guys labeled, but I can look at the two pieces of this and I can say, all right, well, the two parts, 12 times 9, has to be equal to, I look at this guy and I do my two parts there, x times 8. That seems like a pretty simple problem. I'm going to do 12 times 9. I'm going to get 108. Whoops, that should be a times. Divide both sides by 8. I believe I'm going to get a decimal here. X is equal to something like 13.5. Is it all right to have a decimal for this portion of the chord? Of course it is, right? So there's our first example. So part times part equals part times part because the intersection of those two secants is inside the circle. All right. So next example, find x if segment EF, already labeled as 10, EH is 8, FG is 24, and I've got that x on HI. So notice I've got two segments. They happen to be secants. They are intersecting outside here at point E. So this is where I'm going to do exterior segment times the whole equals exterior segment times the whole. So if I just look at this guy right here, the exterior segment is 10 times, don't forget for the whole you have to add, so I'm going to get times 34. On this one over here, exterior is 8. Whole, I have to add these guys, is 8 plus x, or x plus 8. And I can go ahead, distribute, and solve. So 340 equals 64 plus 8x. So when I go ahead and subtract 64 from 340, gosh, there's a lot of hard math today. That would be 276 equals 8x. Divide that by 8, and we are going to get ourselves an answer of 34.5. Again, it's okay to have a 34.5, a decimal on here. As long as you did your math right, you've got it. All right, last but not least, I'm not going to finish this whole problem, but I want to get it set up because we're going to see these a lot. Notice I've got a tangent, and I've also got a secant. So if you like to think of the tangent, it would be tangent squared equals exterior times whole, or exterior times whole equals exterior times whole, whichever one you like better. So I'm going to start on this tangent part. Exterior times whole would be x plus 4 times x plus 4, or tangent squared. I'm going to actually write it out as two pieces. Remember that square just tells us to write it out twice, because that reminds us that we need to FOIL or use the distributive property. Over here, if I look at this segment, exterior times whole, well, the exterior is the x piece. The whole thing is x plus 2, so another 2x plus 2. It doesn't always work out that way. I'm going to put these guys in parentheses because that's going to remind me that I need to distribute. So lots of math here. It's not the end of the world. So when I FOIL this out or use the line method, I get x squared plus 4x plus 4x plus 16. This side I get a 2x squared plus 2x. This is a quadratic, so I'm going to get my x squareds together, and I'm going to get everything on one side of the equation. So I'm going to minus x squared here. I'm going to combine these guys and minus 8x here, and I'm going to minus 16. Hopefully that's not too much at once. That gets me a 0 over here. That gets me an x squared minus 6x minus 16. If you were the factoring sort, you would be looking, my a value is 1, so we'd be looking at what multiplies to negative 16 and adds to negative 6. I know I've got to have an x and an x. I know it's still equal to 0. Pretty sure that would be negative 8 times a positive 2 would get me. Remember, you can always FOIL or distribute that out and check to make sure you did it right. Set each one of those guys equal to 0. So x minus 8 equals 0, so x equals 8. X plus 2 equals 0, so x equals negative 2. And of course, you're going to think to yourself, well, first of all, this segment right here can't be negative 2. And if I put a negative 2 in for that spot up here, that would be a segment of 0. That doesn't even make any sense. So negative 2 is junk. 8 is my final answer. So we've done a couple examples of each one. Hopefully that helps you out. If you've got questions about factoring or quadratic formula, this is a great time to ask about that because it's kind of one of those algebra things that pops up, and here it is. That is it for section 10.7. Thanks for hanging in there. Come in with questions. Let me know how things are going.